Hi, my name is Rebecca Musa. I'm a final year PhD student at University College London, advised by Professors Federica Sarro and Mark Harmon. Today, I'm happy to present a study Federica and I worked on, titled On the Use of Evaluation Measures for Defect Prediction Studies. But first, let's start by talking about viewpoints and angles. And for the sake of this argument, let's draw a shape. Someone looking at this shape from one of its sides might actually classify it as a square. But someone else, looking at it from one of its edges, might say it looks like a diamond. But what if this shape was 3D? And some third person was looking at it from yet another angle and saw it as a pyramid. So which one is it? A square, a diamond, or a pyramid? This, in a nutshell, describes in a very simple way one of the challenges faced by researchers working on defect prediction. Among the pool of measures proposed to assess binary classification models, each describing one or more aspects of the model, which one would you use when evaluating a defect prediction model? But before digging into the evaluation measures, let me just briefly talk about defect prediction and how it works. Software defect prediction is considered an important step towards software quality assurance. It aims to reduce testing cost and effort by flagging possible problematic software components before their deployment. Models applied for binary defect prediction generally exploit past data about software modules in order to classify new ones as either defective or not. Now, an ideal prediction model is one able to reveal as many defects as possible without raising any false alarms. In other words, flagging clean components as defective. But as shown by previous work, achieving this in practice is challenging, given that optimizing for one aspect often compromises the other, especially for problems such as ones with large negative versus positive ratios. On the other hand, defect prediction models with high defect capabilities and high false alarms, or vice versa, models with low defective capabilities but high precision, can still be considered effective depending on the business context. For example, a company developing software for mission-critical systems may prefer to have a model able to identify the highest number of bugs, even if it comes at the cost of high false alarm rates. This also applies to companies which employ automated software testing techniques, making it relatively cheap to accept a high rate of false alarms. On the other hand, if the testing is carried out manually and there is a limited budget, this would be much more expensive. In this case, a company might actually prefer using a model which results in a lower false alarm rate despite revealing a lower number of bugs. Now, these are just some simplified examples, but as you can see that the concept of identifying defects at the cost of false alarms and vice versa really depends on the aim of the company. And the use of appropriate evaluation measures guides practitioners and researchers to understand whether a given prediction model is fit for their purpose or not. Now, unfortunately, the choice of a suitable evaluation measure is still an open challenge faced by the defect prediction community. And a few previous studies have highlighted possible differences resulting from the use of different evaluation measures, with the first one dating back to 2008, highlighting possible threats resulting from the use of different measures. But how has the community reacted to this threat? And what has changed in a timeline of more than 10 years? So we examined a total of 111 defect prediction studies published between 2010 and 2020. In particular, we identified the evaluation measures used in each study, among other aspects, which I will be talking about later on. The results of our survey revealed that there is more than 9 different evaluation measures which have been used to assess defect prediction models over the past 10 years. The most used measures are AUC and F measure, used in 60% and 59% of the papers, respectively, followed by recall and precision. But looking at their definition, measures like AUC and F measure do not portray the full confusion matrix and can lead to biased results when used for assessing classifier performance on unbalanced data sets, which is often the case for defect prediction data. A variety of symmetric and robust measures have also been considered, However, we found that they have been adopted by much fewer studies. For example, MCC was used in only 12% of the studies, G-measure in 11%, G-mean in 8%, and balance in 9% of the studies. We also looked into the number of evaluation measures used in each study. And we found that 30% of the papers analyzed use only one measure to evaluate defect prediction models, among which AUC is the most common, followed by F-measure. Using only one measure might affect the validity of these studies, especially if such measures are among those that have been shown to be problematic. Now, the threat was still present in some studies which have used more than one measure as well. Our results showed that a number of papers use a combination of biased evaluation measures. For example, among the studies which include two evaluation measures, around 30% use AUC and F-measure together. We also found that, despite the warnings raised in previous studies, the use of some of these problematic measures has increased. Again, if we look at AUC and F-measure, we can see that their use has become more frequent with time. On the other hand, no major growth spurt can be seen in the adoption of more robust measures. Finally, we also looked into the rationale behind the choice of the evaluation measures in each of the studies. We analyzed whether a study has explained its use of measures by providing a clear reasoning for their choice, as opposed to just choosing other measures, or when otherwise the reason is obvious from the research context. And we checked whether the study mentions any challenges or threats arising from the choice of the evaluation measures, and to this end, whether any mitigation was put in place. We found that around 60% of studies do not justify the use of the measures based on the aim of the study, neither the models investigated or the data at hand. More than half of the studies also do not acknowledge that using different measures could lead to different results. Among those studies which acknowledge the threat, less than half put in place some form of mitigation. And only 15 out of those recommend the use of unbiased measures, while the majority propose mitigation which might be perceived as unsatisfactory. Now, you can find more details about the procedure we undertook to retrieve these results in our paper. Together, all these findings suggest that some previous studies might have drawn different conclusions had they considered a more comprehensive set of measures. But how significant would the difference in results be had one measure been used as opposed to another? And will a change in evaluation measure really impact or change the conclusion of a given study? To answer these questions, we performed a large empirical study which investigates the 6 most used measures according to our survey. The use of 7 classification techniques, 15 publicly available datasets, validated on 3 different defect prediction scenarios, as well as a more diverse and recent set of data. And for the first time, the comparison is entirely based on a statistical significant test and the effect size measure. So we posed 2 research questions. To address our Q1, we first produce a ranking of the prediction techniques per measure according to the Wilcoxon signed rank test and a non-parametric effect size, A12. Then, based on these rankings, we compute the ranking disagreement for each measure by counting the number of times it produces the same ranking with respect to using other measures. This tells us the extent to which a measure agrees with the others. Now, if the rank disagreement of a given measure is high, this would suggest that there's a non-trivial error when using different measures. Our second research question analyzes this error at a finer grain to gather further insights on the extent to which these rankings differ. So we investigate the rank disruption, which describes the percentage of cases in which a rank of a specific technique, based on a given measure, changes when assessed using the other measures. We found that there is no case where all evaluation measures produce the same ranking. In fact, the evaluation measures produce a unique ranking in 83% and 85% of the cases, according to the Wilcoxon test and the A12 effect size, respectively. We also observed that the number of cases where at most 3 evaluation measures provide the same ranking is less than 1%. And even in those very few cases, it is not always the same set of evaluation measures that agree on a ranking. Now, we also perform a more fine-grained analysis of our results to get a better understanding of the impact the use of these different evaluation measures can have on the conclusion validity of a study. So we examined the rank disruption of each evaluation measure when considering the top rank techniques. For example, here we show the results of the average rank disruption of the top 3 rank techniques. We can see that the disruption remains very high when considering the top three rank techniques for each scenario. According to the Wilcoxon test, the rank disruption ranges from 76% to 93% when evaluating the within project scenario, from 68% to 93% in the cross-version scenario, and from 64% to 96% in the cross-project scenario. And very similar observations also hold when analyzing the rank disruption based on the effect size measure. So basically, the main takeaways are that despite the warnings raised in previous work, the results of our literature review reveal that the choice of evaluation measures is still a major concern in the community, and that it has only been partially tackled so far. Our review of previous work published over the last decade has also revealed that the majority of the studies do not provide a rationale for the measures. They often use measures which only partially reflect the performance of defect prediction models, and that the measures used are often the most susceptible ones to data imbalance. Our empirical study also suggests that in the majority of the cases, a prediction technique that would be believed to be better than others when using a given evaluation measure becomes worse when using a different one. We saw that the rank disruption of top-ranked techniques is just as significant as when all ranks are studied, making the results even more striking. We hope that this evidence will encourage the community to act upon this matter and carefully select the measures based on factors which are specific to the problem at hand. These include the class distribution of the training data, the way in which the model will be used, and the way in which the model has been built. We also recommend to include at least one measure among the set used which is able to capture the full picture of the confusion matrix so that it is possible to assess whether proposals made in previous work can also be applied for purposes different than the ones they were originally intended for. And whenever possible, we also recommend that researchers make the raw confusion matrix publicly available, as this can enable other researchers to compute any measure of interest, and it makes it easier for them to draw meaningful observations across different studies. Thanks a lot for listening. This is it for now.